A commercial cargo ship is essentially a massive hollow steel box. It has a strictly fixed three-dimensional geometric volume. But the ocean doesn't care about volume. The ocean reacts to physical mass. When a crew loads a vessel, they face a strict physical constraint. They must translate the empty space inside that steel box into an exact weight of cargo. Pack in too much mass, and the hull breaks under the stress. Pack too little, and the voyage loses money. The mathematical bridge between theoretical geometry and physical weight is density. Density measures how tightly matter is packed together, defined specifically as mass per unit volume. This equation shows the bedrock of fluid logistics. Weight equals volume multiplied by density. Calculating this precise volumetric conversion ensures a vessel operates safely. Get the math right, and the ship maximizes its cargo hold. Get it wrong, and the resulting overload can trigger a catastrophic structural failure. Every fluid calculation in marine engineering starts with a single, universal baseline: fresh water. The metric system gives fresh water an incredibly elegant density. 1 cubic meter of fresh water weighs exactly 1,000 kilograms. Because 1,000 kilograms equals 1 metric ton, this standard translates perfectly to the maritime tonnage system. The density of fresh water is exactly 1 metric ton per cubic meter. This visualization demonstrates the operational advantage of that constant. It creates a perfect 1-to-1 ratio. If a tank holds 120 cubic meters of fresh water, it holds exactly 120 tons of mass. Thanks to this mathematical symmetry, fresh water provides a frictionless starting point. Navigators use it to anchor all the complex tonnage calculations required across the shipping industry. But ships rarely carry pure freshwater. They hold a wide variety of liquids, ranging from heavy seawater pumped into ballast tanks to light aviation fuels stored for transport. This formula introduces relative density, also known as specific gravity. Relative density is a mathematical ratio used to adjust calculations for these varying fluid weights. The concept is straightforward. It compares the weight of a given substance against the weight of an exactly equal volume of fresh water. Look at this diagram. It shows 3 identical volumes of water interacting with different materials. The cork, the wood, and the aluminum all occupy the exact same physical space, but they displace entirely different amounts of physical mass due to their unique densities. Since the density of fresh water is exactly 1 ton per cubic meter, marine engineers get a powerful mathematical shortcut. The relative density acts as a direct, dimensionless multiplier. This table shows how that plays out. Salt water has a relative density of 1.025, which yields exactly 1.025 tons per cubic meter. Heavy fuel oil typically registers a relative density around 0.9, meaning it weighs 0.9 tons per cubic meter. Applying this multiplier means a navigator can swap out cargo variables for any liquid. They determine the exact mass of the load without ever needing to recalculate the fixed geometric architecture of the ship's tanks. Knowing the density of the fluid is only the first step. The equation must also account for the physical constraints of the steel tanks holding that liquid. A theoretical calculation of a tank's maximum volume doesn't work in practice. Engineers must factor in physical clearance requirements, a concept known as ullage. Ullage is the precise measurement of the empty space deliberately left between the surface of the liquid and the ceiling of the tank. This diagram illustrates a practical scenario. We have a tank measuring 20 meters long by 24 meters wide, with a total physical depth of 10.5 meters. Although the tank is 10.5 meters deep, an assigned ullage of 2.5 meters restricts the functional fluid height. That leaves exactly 8 meters of loadable depth, giving us an operational volume of 3,480 cubic meters. Now we apply the relative density multiplier. Taking the oil's relative density of 0.84 and multiplying it by that 3,480 cubic meter volume yields the final mass, 3,225.6 tons. Factoring in ullage allows engineers to guarantee the mandatory empty clearance required for safety, while simultaneously locking in the exact physical weight pressing down on the ship's hull. That empty clearance exists specifically to absorb the most volatile variable in fluid logistics, dynamic thermal expansion. As liquids heat up, particularly heavy fuel oils sitting adjacent to active engine rooms, they physically swell. Their mass remains the same, but their geometric volume increases. To prevent disaster, Maritime protocol dictates that a specific mathematical percentage of the loaded oil's volume must be left entirely empty to accommodate the swelling. This equation addresses that constraint. Here, we have a tank with a known maximum capacity of exactly 153 cubic meters. The rule requires a 2% allowance for expansion. You cannot simply load 153 cubic meters of oil and subtract 2%. The total available tank space must equal the oil's volume plus 2% of that specific, currently unknown oil volume. Algebra resolves the trap. The 153 cubic meter tank actually represents 102% of the safe loadable oil capacity. Dividing 153 by 1.02 reveals that the safe volume to load is exactly 150 cubic meters. Finally, we convert that safe 150 cubic meter volume into physical mass. Using the oil's relative density of 0.8, the final safe load comes out to exactly 120 tons. Ignoring the algebraic reality of thermal expansion leads directly to burst bulkheads, ruptured piping, and massive environmental spills. The math protects the structural integrity of the ship. Calculating cargo and ballast capacity is a rigorous, multi-layered workflow. Every computation relies on the universal one-to-one baseline of fresh water to map three-dimensional geometry directly to physical mass. The dimensionless relative density multiplier then scales that baseline to account for the actual fluid on board, whether that's dense seawater or light petroleum. From there, required ullage gaps and precise thermal expansion percentages carve away the theoretical geometry to establish hard physical operating limits. Look at this list of exercises. A commercial vessel contains dozens of distinct tanks, and engineers must execute these precise algebraic deductions for every single one of them before the ship is cleared to leave port. These formulas govern the physical reality of thousands of tons of moving liquid. Their strict daily application forms the precise dividing line between maximum commercial efficiency and total structural failure on the open ocean.